Hey everyone. Today we're going to be looking at a clear explanation of how bubble sorts work, see how to correctly structure an exam answer to get full marks, and finally, understand the time and space complexity with big O notation. This will set you up perfectly for the next video, where we'll program a bubble sort in Python. But before that, let's jump straight into how they work. I have an unordered list here, and I'd like to put it into ascending order. We can use a bubble sort. The bubble travels from left to right, dragging the higher numbers with it. It will pass over the list multiple times, so I'll write down pass 1. This will all become clear in just a moment. The bubble starts by surrounding the first two elements. Let's call these left and right. We're ordering the list from low to high, so if left is greater than right, we swap. The bubble moves on and compares the second and third elements in the list. Same premise again. If the left element in the bubble is greater than the right, we swap. As 4 is lower than 5, we don't this time, and we just move on. On to the next pair. 5 is greater than 3, so we swap. Hopefully you're getting the gist by now. We move on again. 5 is not greater than 6, so we move on. 6 is greater than 2, so we swap. We have no more elements to the right to compare 6 to, meaning we have completed our first pass. This means the bubble has passed over the list for the first time. As you can see, our list isn't in order yet. This is why we'll need to do pass 2 in just a moment. Before that, however, let me point out one thing. After each pass, the highest unsorted element in the list will now be sorted. This will make more sense after the next pass. But as you can see, our highest element, 6, is now in the correct place. Now on to pass 2. We do the same thing again, starting with the first two elements. No swap, swap, no swap, swap, no swap. Pass 2 is now complete. Since 6 was already sorted, the highest number which is now sorted is 5. On to pass 3. I'm sure you don't need my narration for this one. Pass 4. Now this is really important. We can clearly see that the list is in order. However, since the bubble made a swap on its last pass, the bubble doesn't know if the list is in order or not. The bubble only knows that the list is in order when no swaps have been made. This means we'll do one more pass. No swaps were made, so the bubble sort is complete. Now this is all well and good watching it like this, but you can't exactly take bubble mixture into an exam. So how would you tackle an exam question? For GCSEs, A-levels, and I'm sure plenty of non-UK qualifications, you'll need to answer a question like this. Show each stage of a bubble sort to sort this data into ascending numerical order. You may also get a question involving strings, but don't worry, that's the equivalent of putting them in alphabetical order. What's great about these questions is we don't need to write in plain English. Firstly, we compare the elements to see if the left one is greater, etc. We can literally just write out the state of the list after each swap. What is vital here is that we must keep track of where we are in the list, because if we start a new pass before finishing our last one, we'll likely get the wrong answer. Once again, we start with the first two elements. In this case, we do need to swap them. It doesn't hurt to underline them. You won't lose or gain marks, but it will help you keep track. Let's rewrite this whole list with these two elements swapped. Looking at where we had underlined in the previous list, let's move on to the next two elements, 7 and 2. They need swapping, so same thing again, underline and rewrite. Moving on again, we have 7 and 9. This time they don't need swapping, so we should not underline and rewrite them. We should just move on to the next pair. 9 and 5 do need to swap, so let's rewrite. We have now compared the last pair in the list, so we need to do something vital to get marks. We need to write something to highlight that this was pass 1. This is a nice way of emphasising it, but if you can't draw curly brackets, then write end of pass 1 next to the final line. We are now going to continue with pass 2, of course starting with the first pair. Let's highlight pass 2. Next, pass 3. Now well done to any of you who've realised we haven't finished yet. Since we made a swap on the last pass, the algorithm will keep going. We'll compare each of the elements, realise that no swaps are made, but we should still write out the list again and label it pass 4 so we can get full marks. If you think that was way too easy and long-winded, it is also perfectly acceptable to write it like this, where we only write the final result of each pass, omitting the individual swaps. But if you make a tiny mistake, you may not get follow-through marks, so it's at your own risk. Finally, everyone's favourite part, big O notation. It may seem daunting, but I'm going to break it down in a way so that hopefully everything clicks into place. Let's start with the space complexity, as I believe that's much easier to grasp. The space complexity is the amount of memory we'll need to execute the bubble sort. However, this does not include the memory needed to store the original list in the first place. Despite my beautiful swapping animation, in reality, when we swap two values, we need a temporary variable to stop them from overwriting each other. I'll explain this further in my next video, but that's not vital right now. What's beneficial about this temp variable is we can use it for the whole list on every pass. At no point do we create extra lists or make recursive calls. We only ever need one additional variable, temp. This means the space complexity is O of 1, no matter if it's best case, worst case, or average case. This means the bubble sort has great space efficiency. This is basically as good as it gets. Let's now look at the time complexity. We can think of time complexity as the number of operations needed to run an algorithm, i.e. the amount of time the algorithm takes. We measure this relative to the input size, or the length of the list, which we call n. I have 3 lists of different lengths here to help us conceptualize how this works. To figure out n, we simply count up the number of elements. When the bubble passes over the first list, we make 1, 2, 3 comparisons. We make this many for these 2 lists. What do you notice about the number of comparisons compared to n? It is always 1 less, so we can say, as a general case, n-1 comparisons are made on each pass. The reason it's n-1 and not n is because every index will have a go at being the left element in the bubble, except the very last one, as we have nothing to the right of it to compare it to. So, we have n-1 for a single pass. However, with big O notation, we must take the highest order. What this means is if we have multiple terms added together, we use the highest one. As you can see here, n is higher than constants, such as 1 or -1, so we can simplify this to n. We're not done yet. This has given us the time complexity of a single pass, and that's not what we're after. Let's look at the first list we had. For a bubble sort, the worst case scenario for an ascending list is a list in reverse order. Actually, anything with the smallest element on the far right is just as bad, but let's only focus on one example. Let me show you the state of this list after each pass. It has taken us 4 passes to get to the correct answer. What's special about the number 4 in this case? It is n. If we had 7 numbers, it would take 7 passes. 100 numbers, 100 passes, and so on. You could argue that since it is the worst case, it'll actually take n-1 passes to get a sorted list. But once again, we'll be taking the highest order, so we can forget about that. So, if we make n comparisons on each pass, and in the worst case scenario, we make n passes, we have to multiply these together to get the total number of comparisons, n squared. This means the worst case time complexity of a bubble sort is O of n squared. This is really bad for long lists, as it gets large really quickly. And as you'll see in my other videos, there are much faster sorts. The best case scenario for a bubble sort is a list which is already in order. As before, we'll make n comparisons on the first pass. However, I mentioned previously that when no swaps are made, the algorithm stops. We have made n comparisons, but only done one pass. N times 1 is n, so the best case time complexity is O of n. Although this is great, in reality, we often don't really care about best case scenarios. But I guess you could argue that a bubble sort could be good for checking whether a list is already in order. As for the average case, although we're obviously going to have fewer passes than in the worst case, it is still a very large number, and as we ignore constants and lower order terms, our complexity remains at O of n squared. That was a lot, so here are the complexities if you've forgotten. I thought I'd be fancy by putting omega and theta, but if you're doing A-level, ignore that and just put O. One quick last thing, since I reckon some people will mention it in the comments if I don't address it, but we'll be going into it properly in the next video. As I briefly mentioned before, after each pass, the new highest element is in the correct place. This means we can actually save time by not comparing it on the next pass. This means the algorithm will make one fewer comparison on each pass. By the time we get to the last few passes, we'll only be making a few comparisons. This will actually mean we roughly cut our total number of comparisons in half. This is very beneficial for smaller lists. Despite this, we're essentially making our complexity O of 0.5 n squared, but we always ignore constants, so this remains at O of n squared. That was a lot, but now you know bubble sorts inside out, you're fully prepared for my next video, where we'll be coding one in Python. This took time to animate and script, so if this helped you, it would be great if you liked and subscribed. Let me know in the comments if you need anything clarifying, and what you'd like to see explained next.